one should just adjoin them to O. And actually, I didn't mention this, but this O that I claimed exists actually can be made to contain all the constants. I just didn't mention it. It's part of the, it's not here, of course. Here you cannot do this.
I see.
But here you can.
Yeah.
You can arrange that O has all the constants of R.
Right. It's like assuming constants are algebraically close.
Yes, exactly.
Yeah. But if you have a normal subgroup of the Galois group of O of U over O, and you look at its fixed ring, does that fixed ring finitely generated over O?
I don't know. I never looked.
So in other words, would you be able to say the analog of P Carvesio over the fixed ring of a normal subgroup is P Carvesio over the ground field?
The plain answer is I have no idea. I just didn't. I couldn't do much, and I actually stopped thinking because I thought about other things. But I felt I really need to understand this ring here.
Yeah.
And
start there and go up.
Yeah, exactly. And I made some computations related to it. I convinced myself that these guys are not equal. They shouldn't be in general. And I convinced myself that this is interesting and it relates to nice invariant theory, classical invariant theory, just 19th century. It should look like that. But I didn't quite pursue this.
Oh, so G is the Galois group of the extension.
Yeah, of this whole thing.
And so, I lost that, missed that. So, so the fixed ring is not the graph.
Right. So that's how the Galois correspondence fails.
And so you were wondering what the significance of the elements of the fixed ring is.
Yeah. So this is what I call the gap between GLN of R and GLN of F1 bar. The gap is filled here.
Yeah.
And philosophically, it's an interesting thing. You see, there's this philosophy of varieties descending to the field with one element.
And what does that mean?
That's a good question. That means that if you take points of the variety with entries 0 or roots of unity, you get so many of them that in some sense, if you put some more structure on this set, you can reobtain the whole variety. But that's not quite the case with GLN. In GLN, if you take the entries, the variety, you can consider n by n matrices with entries 0 and roots of unity. They don't form a group. Isn't it? If you have two matrices with roots of unity and 0, you multiply them, they don't. So that's not the right definition of the points with entries in F1 bar of GLN. This is the right definition. But then the Zariski closure of this is that, not the whole of GLN. That's the gap that I was talking about.
Oh, that is a gap.
Yeah, that's a big gap. And this sort of is the reason, I guess, why people say that GLN does not descend to F1.
No.
Other guys do, but he doesn't.
GLN does not. Whereas in the usual field.
Yeah, other things do.
Certainly.
GLN does not. In differential algebra, it descends to constants.
Yeah.
But in arithmetic, GLN does not descend to F1. The affine space does descend to F1, but if you take out the 0 locus of the determinant, that does not descend to F1 anymore. Because the determinant is not a monomial thing, it's a complicated thing. So I think that's the way people think about these things.
Yeah. What if you move all the way down to GL1 and analyze that? Can you analyze that whole picture?
Say it again.
Take n equal 1.
Yeah.
and look at the subgroups of the multiple.
For n equals 1, I think everything works just wonderful.
Galois.
Yeah. Especially because you have
you're already down to. Yeah. That's amazing that that analog exists.
The analog of Gn goes to Ga. That exists and takes care of everything.
Oh, that's why.
Yeah.
And you just pull it up, and in a sense,
exactly.
once you have the logarithmic derivative,
your theory
you have the exponential in disguise.
Exactly. Works.
So that's an anomaly. So if you just
GL2 already. No, it's but that's the way things are. I mean, what can you do? So that's
it makes it more interesting.
So there's no.
That's good.
Yeah. The determinant is not a monomial. We all know this.
No, too bad.
Yeah. No, it's good.
It's good.
Yeah. And SON, SPN are even crazier. They have their own things going on.
No. This question's a little bit random, but what if you looked at the group that's sort of in between SLN and GLN, where you demand that all the matrices have determinant and root of unity instead of just one?
Yeah, you can do that.
And is that maybe like in some ways a more reasonable version of GLN, or?
The determinant is a root of unity. Is something? It appears in my. This condition appears in my paper. Yeah. Okay. So one can consider that. Yeah.
What about a more general thing, that the determinant lives in one of those subgroups of GM?
Yeah.
That would be a subgroup that sits in between the two more.
Sure. This is like so you want to. This is like a disguised. The context that we're talking about is actually a GM story. Yeah. So it's not a genuinely, GL2 or GL3 story. It's a GL1 story.
GL1 story.
Yeah. So it's sure one can do that, and
But what's so interesting is that so central is the normalizer of a maximal torus.
Yeah, that's
it's
fine.
Sort of almost getting you close to GM.
Yeah. So an easy exercise for preschool is if you have over the complex numbers, if you have that x, y, p is xp, yp for all y, that implies that x is in this n, and vice versa. So that's why. Raising to the power p commutes with multiplication for any y. That happens only for x in the normalizer of the maximum torus. So that explains somehow what's going on.
I have another question. When you had to modify the notion of cocycle amongst other things, does that correspond to? I mean, do they classify main homogeneous spaces? Is there a version of that story here, or?
I don't know. Yeah, I don't know. Yeah, that I haven't looked at. Yeah, just. Sure. I mean, that's a good question. Yeah. Mm-hmm.
You can tell us anything about curvature?
I can. It's up to you guys. Depends on how long you want to be here. Yeah, okay. Say a few words. So the problem is to implement several primes into this picture. So you need a ring. So let's give some definition. So you have a ring, A, and let's say that you have a collection of p derivations, one for each prime. And let's say that you have a family of primes, I want to call it script p. So these are p derivations on A. Then you can define the commutator as follows. It's an easy thing. So I'm going to take two primes, P and P star. And this is a map from A to A. And it's given by a formula that can be demystified again. It's easy to explain. But here is the formula. Delta P star of A. But it's important to have it in this non-demystified because for technical reasons, that's the thing that one needs to consider. So this would be the usual commutator, but actually you need to correct this as before by adding a polynomial in lower order things. And I want to tell you what the polynomial is. CPP star, it's a polynomial in three variables, x0, say, x1, x2. And this is like boring, so CP star of x0 with a p. It's a long thing, I might not even write the whole thing. There's one more term, and there are two more terms. Let me write one more. There's a term that looks like this, and there's a term that looks like that. X2 to the p plus, and one more term that looks like this. So there's a polynomial in three variables, and you have to add it. And you have this, the demystification of this is simply that if you multiply by pp star this thing, you just get the commutator of the lifts of Frobenius, so that's all. But for the purposes of, for technical purposes, you really need to know this and not only that. Because you may have torsion, you always do have torsion when you mod out by powers of p, and that you need to do. But this this can be used to show that this is additive actually. So this is additive. Okay. So you have this expression, you call it commutator. And then if you have a family of p derivations, you can consider its commutators. These are some linear maps, and you seem to have a concept of curvature. But actually, you don't, because in all the interesting situations, the maps are not on the same ring. So let me give the next definition. So in all, this is like almost like a joke. This is the real thing. So let's say a connection, you can call it a connection or whatever, an arithmetic connection on A is a family not of p derivations on A, but each is on the p-adic completion of A. So delta p is from A p into itself, a p derivation. This is how things appear in nature. So, for instance, for the main examples being for phi g attached to SO or SP that we saw before, they are lifts of Frobenius on the p-adic completion of the ring of GLN, not on the ring of GLN itself. They really involve series. So they're not on the same ring, so you cannot take the commutator. So what do? I'll tell you what you do. You find a ring where they all act. And there is one such ring. So let's say that you come up with a definition and say the following thing. Let's take an easy situation where you have an A algebra like this and a surjection like that. So now I'm kind of changing the ring. So the main A has, let's say that A has a family of things that commute. So delta P on A, not A hat, but A, they commute. For instance, A can be Z easily. So that's the most interesting case. Or Z, ring of fractions of Z. And let's say that, so this is not a connection, but really a, what one can call a global connection. It's like the delta P's are defined on A. But let's say that the delta P on B is just a connection in the sense that each delta P is on BP. What happens in practice, for instance, so this is a fun thing that happens in examples like this, like that, and in many other examples, like examples that have to do with elliptic curves. It seems to happen all the time. You see, this is like a scheme over spec A, and this gives like an A point of that scheme. Yeah. And let's say that this is pi, and you take the kernel. And now hold on to what I'm going to say, because it's going to hurt. So, maybe I should make a picture. This is spec A. This is spec B. I use this in other papers too. I have one paper with Jim Borger, another one with another collaborators. That's a funny thing. So if you have two primes, and this may be inspiring for you for other reasons. So when you periodically complete spec B, you are like in a tubular neighborhood of this. So this is like full of B periodically completed. And this is like a tubular neighborhood. You know what I'm going to do. I'm just going to draw instead of write mathematics, because that's more, it's a better idea. This is like full of P star adequately completed. And there is absolutely no relation between them, of course. But what happens is that if you have a section like this, what you can do is take a tubular neighborhood of that section. And let's call this full of B I adequately completed, where I is the kernel. So then look what you can do. Delta P induces a delta P on the following thing. You periodically complete, and then you I adequately complete. And very strange. Well, it's not so strange, because you are somewhere here. And that doesn't seem to help, isn't it? It's not not very helpful. But if I is generated by a regular sequence, and that happens all the time in algebraic geometry, so I is generated by a regular sequence, then actually the I-adic completion sits inside this. So this happens most of the time.
And that's all you need to ask from I? It doesn't need to be compatible with the delta p in any way? Or?
Did I say, oh, yeah, sure. Yeah. I forgot to say that I will ask about I to be preserved by delta p. So delta p, I, b hat p, is inside I, b hat, thank you. Yeah, I assume this for all p. Yeah. This is a very important point. Yeah, so the flow preserves the section. This is important in many ways, but yeah, so the flow preserves the section. You have to think of B as being GLN over A, and this is the identity section. So this is the unit of the group. But then, of course, look what happens. Delta P star has the same property. Delta P star is defined on B P star I, and this guy also contains Bi, like this. So you can ask, can it be maybe, so this delta P star acts on this, delta P acts on that. Can it be, are there cases when actually delta P sends this into itself? Because maybe then this also sends this into itself, and then you compare them on Bi hat. And there are. This happens all the time. In all the interesting examples, actually delta P sends this into itself, and this into delta P star sends this into itself. For instance, this happens with these connections that we constructed last time in the previous lecture. And then you can compare them. Take the P star on this ring, Bi hat. And now let me tell you what happens. These are just some additive maps from Bi hat into itself. But what is Bi hat? It's just a ring of power series over A. That's what is going to happen. And these guys induce, I'm going to put a star here, maps like this. I'm going to assume that I is reduced. Or I don't have to assume. I assume something else, so I don't need to do that. So star, these guys induce maps from I over I to the nu into itself for all nu. This is like the conorm for nu equals 2. This would be the conormal bundle. So, and it's an A module, finely generated A module. So these are just matrices with entries in A. That's all that they are. If A is Z, they are matrices with Z coefficients. And, but what happens, something interesting happens, is that for nu equals 2, these may turn out to be 0. For nu large enough, they're not 0. But there will be a nu such that, so there is a nu such that we get that this map is 0 for nu minus 1, and it's not 0 for nu, so you get a map like this. And this is the new symmetric power of I over I squared. These are the interesting guys. So these are some linear maps from the conormal bundle to some symmetric power of it. Nu depends on P. For each P you have another nu. It's the minimal nu that you get. And the P star, of course. So this is delta P star. Induced by this, and I could call it F like in physics, you know, the curvature with a nu here. Maybe I should call it like this, nu. So you come up with some. This is like a Z module of finite rank. This is a Z module of finite rank. Everything is finite rank. These are just some matrices with Z coefficients if A is Z, or a ring of fractions of Z, as is in our case. And one can try to see what these are in the examples of curvatures that we have. And so far I just have a theorem saying that for phi on GLN with n at least 4, I couldn't do it for 2 and 3. My trick doesn't work. Attached to SON or SBN, the way I showed you in the last example, the last lecture. These maps are actually non-zero at level PP star. If P is different from, so the curvature doesn't vanish, and this is the level where it doesn't vanish. So you have a curvature attached to these flows that we talked about in the last lecture. But the funny thing is, if my computations last night are correct, the curvature at level 2 vanishes. At level 2 would be from I mod I squared into I squared mod I3. That vanishes. So the non-vanishing happens later, but I don't know where. So
it's a bit there, but it could be sooner, maybe.
Yeah. Yeah, so this could be sooner, but not sooner than 2. So you have these computations of curvatures for various connections. So once again, the main point that I want to make is this, that very often in this theory, you have p derivations on rings that are not comparable, because each delta p is a p derivation on p-adic completion and p varies. These guys are not comparable. But if you have a section, sometimes the induced derivation in here actually is induced by a p derivation on the whole of the tubular neighborhood of the section. And the same thing happens with this. The p derivation induced on this completion extends to a p derivation on the whole tubular neighborhood that I drew here. So you can compare them on this tubular neighborhood. And this happens all the time. It's like somebody did it on purpose. So, yeah, to make me happy. So you can do things like this. You can ask, what happens if you have another? I did it in another paper, and there is a monodromy. If you do this, do this, do this, and come back, you don't get the same thing. This is like you feel like you want to eat it. Because it's very interesting. So what's going on? What kind of monodromy is this? And the period that you get is transcendental over ZP, over ZP. It's an element in bit ring corresponding to the algebraic closure, which is transcendental over ZP. So there are interesting phenomena here, but for the purpose of curvature, one section is enough because it's usually the identities. Okay, so that's the story, the curvature story.
I have a question about the color theory. So, what would you like to achieve with the color group? What would you like to find out?
Yeah, what? So the Galois group has to control algebraic relations among the solutions, as usual, like in the algebraic, in the usual Picard-Bessian theory. So yeah, but I don't know what to say now. Yeah, so it should be something that controls the algebraic relations among solutions of equations of that sort that I mentioned. And it seems to the Galois group seems to be closely related to the dynamics in Pn that is related to these equations the way I explained. So this, you know, they have this algebraic dynamics, like Spiro, who is in this building, looks at these things. So if you look at this, or more generally, endomorphisms of the form phi of x, as in the previous lecture, the arithmetic dynamics of these things on Pn is closely related to these Galois groups. So there must be that's the kind of waters where these things float. So these Galois groups will detect something about the algebraic dynamics of these maps. However, this is a twisted thing. It's not what the people in algebraic dynamics look at, because you have this p derivation. You have this twist given by the differential thing. So it's something, so these Galois groups should capture something like a differential arithmetic dynamics. I said it. I have a word for it. Yeah, so something like that. It's a sort of differential arithmetic dynamics. If you ask what is this good for, I can immediately ask what's arithmetic dynamics good for. So it's the same old story that we're all facing. So what are our dreams good for anyway? So, but yeah, this is the kind of thing that this measures.
And does the lack of complete Galois correspondence stop you from getting results?
I don't think so, no. Because, as I mentioned, there's this intermediate guy that does not coincide with the bottom guy. But I expect that things in between this intermediate guy and the big guy will have a Galois correspondence. It's just that I never really computed the intermediate guy. And, yeah, this has to be related to the invariance of the action of, let's place ourselves over C, and then the normalizer of the maximum of the diagonal torus in GLN C will act on C of x and the determinant of x minus 1. So you can consider the invariants.
What's the question?
Can you say anything about Grothendieck's P curvature? No. No. And the answer is, and let me explain, the Grothendieck's P curvature, anybody? I can talk, I'm actually talking.
Let's read the whole question because not everyone can see it actually.
Yeah. Can you say anything about Grothendieck's P curvature conjecture from this perspective? The answer is, I think, is no, simply because the Grothendieck P curvature conjecture is about usual differential equations with respect to usual derivations of functions, whereas all this theory is about P derivations of numbers.
Yeah.
So not usual derivations, but Fermat quotients of numbers. Instead of derivations of functions, you take Fermat quotients of numbers. So the derivation is in the arithmetic direction, not in the geometric direction. Yeah. So I think the two directions are very different. The direction of in which you take the derivative is different. This is about taking Fermat quotients of numbers, and his conjecture is about usual differential equations, linear differential equations.
Is this question from Ray or someone else?
Anonymous.
No.
Anonymous.
Maybe we'll see the name in a minute.
But I love this thing. Suddenly somebody asks a question.
Isn't that great?
Yeah.
Two questions.
Maybe we'll see the name in a minute.
Yeah. Yeah, the Fontaine rings are a whole story in themselves. So there are, when Fontaine, I'm talking about Ray Hubler's question, when Fontaine introduced his rings, there was a very mysterious part of his construction. The addition on those rings was defined through a certain limit, etc. But nowadays, people found a better pure Witt theoretic construction of those rings. So things are much less mysterious. So today, these rings are really part of Witt theory. So they should fit very well into this kind of picture. It's just that the flavor of the period seems to be different, if I understand Manin correctly.
I wanted to ask you about a comment you made at the beginning about having some applications to Heegner points.
Yeah.
I know very little about them except that they come up as an example of Euler systems and connection with Polyvagin's work. Would your applications have anything to do with that, or some other aspect of Heegner points?
The applications, once again, they come from the interplay between P derivations and elliptic curves and modular curves, not GLN. So that's the first thing that I want to say. And secondly, the applications don't have something directly related, are not directly related to Polyvagin systems, but they are related to the modular parametrizations. All that the applications that I was talking about are related to is the maps between modular curves and elliptic curves, and the arithmetic differential equations on this and on that, and the way modular parametrizations are compatible with those arithmetic differential equations. So there is, in this theory, there is a concept of jet space. And if you take a modular parametrization in the sense of Eichler and Shimura, this is a map So it has an integral model, so you can apply the arithmetic jet functors like this. And then this has a money map. I told you about the arithmetic money map. So there are homomorphisms between the nth jet space of E and the additive group, which is the line. So you suddenly have some wonderful maps between the jet spaces of modular curves and the line. And you can use them to prove certain finiteness theorems for Heegner points. So that's the way it works. The Heegner points being the images via this map of the CM points here. So if you take this locus of CM points, you can map it to a set H, and H, the set H can be viewed as a set of Heegner points. Actually, the general Heegner points are obtained from elements of H by applying a trace. But even if you don't apply a trace, people still call the elements of H Heegner points. And these are the points that you can study using this map, the composition of the map induced by the modular parametrization with the arithmetic Manin map. This one, once again, is a story that's perpendicular, of course, to the story of today, because the story of today was about GLN, which is supposed to be the easy one. Yeah. And it is easier in some sense because the objects are easier, but I have no arithmetic applications of the story that I told you today. So there is.
Oh, I'm sorry.
I have no arithmetic application
that's
of the story.
Diophantine.
No Diophantine application of anything. Also, I'm not aware of any Diophantine problem on GLN that might be attacked via this kind of thing.
The Galois groups, because they're contained in n upper delta, are sort of almost like analogs of differential algebraic groups. So do you have more general differential algebraic analogs in this theory?
No.
No.
So I did not really. So I have a student who produced some interesting examples of differential algebraic groups in this theory. They are really contorted differential abelian subgroups of GLN, but embedded in crazy ways using the Fermat quotient, the P derivations. So there are things like this. One typical example that everybody here will recognize is, so you can take GM and embed it into GL2 by sending
I know.
A
delta A?
Instead of delta A, you will take A psi of A, 0A, and psi is the thing that I wrote before, because of course the analog would be delta A over A and A cancel, and you're left with a. And there are GLN versions of that. So there are many examples like this due to the presence of psi. But in some sense, they're all explained by psi. This is related to your work too, of course, because you have these representations of. Yes.
So would you have a parametric theory of Galois theory?
Oh, no. We don't have a Galois theory. There's no Galois theory, but there are some groups floating around. That's all I have.
Feeling lonely?
Just
the groups.
Every group floats in one direction.
Okay. Very nice.
You studied more from the representation theory?
No, no. All I know about is these examples that my student wrote down, that they're all elaboration of this. You can have more complicated things, as I said. Instead of 2, you can have an n, and you have upper triangular matrices with entries cooked up from psi and psi squared. They look like Leibniz stuff, that you're very familiar with in differential case. Yeah. So these things do have an analog, but they're all once again explained by this psi. So whenever you have a map from GM to GA, like in differential algebra, you can create these things. Yeah, and the derivation. In this case, you have psi and phi. You can play with psi and phi and create such representations. But no theory, just some examples. But that's interesting. I think the most important thing is to have some examples first, and then you can create a theory around them. So there should be some nice theory.
Would this possibly fit into Moshe Kaminsky's Galois theory of operators?
I talked to him in the past. I don't think so. No. I don't think so. There is a problem with the whole. This is a little bit too non-linear to fit. In my impression, my impression is that it's a little too non-linear to fit into. Yeah. So there's no Hopf thing in the background that I'm aware of, unless. I will study more those papers by that Russian author that Manin told me about, Witt rings of non-commutative Witt theory. But he was mentioning that in relation to something slightly different, not in relation to Hopf algebra, the Hopf algebra story, but with the attempt to construct a Poisson formalism. So the problem is, does one have a Poisson formalism in which derivations are replaced by p derivations? Okay. Yeah, that's it. Because I wrote this paper with Manin on Pain-Levé, maybe and there we have an analog of the Hamiltonian formalism for Pain-Levé that exists in the arithmetic case. So we have the Hamiltonian, but not the Poissonian. The question was, is there a Poisson formalism? That would be fun, but
I wasn't sure if you were asking about Kamenskий's work on a Tanakian theory with operators, or he recently came to the coaching seminar and he was presenting this work on kind of bypassing the Tanakian formalism altogether, and it looked.
Yeah, well, with that I'm not familiar actually. Yeah, I should ask him. Yeah. What is the theory of bit vectors over non-commutative rings? Basically, we're referring to him. No, I was not referring to him. I am familiar with a lot of Lars's work, but let me see this. He has a theory of bit vectors over non-commutative rings in his homology theory. No, I'm not familiar with that. Although I'm familiar with quite a few of his papers, I kind of know him well. Okay, I'll take a look. Yeah, I was not referring to that, no. Maybe I should talk to I was not referring to that. I was referring to papers by a Russian mathematician, I forgot his name now, who is, I think, at the club. If I understand correctly from him. Okay, I'll take a look.
Another anonymous comment.
Yeah. That's fun. I love it.
Isn't it?
Yeah.
I love it because they're very good questions, very pertinent questions.
Yeah.
Very pertinent. So all three are excellent questions. Yeah.
Is there another questions come?
Maybe.
Yeah, the P curvature question is, I could go back to it a little and say that P curvature is a concept, of course, about usual differential equations in characteristic P. But there may be a lift to characteristic 0 of that concept, and I could never find it. So, but that's a good question, and that could fit into what we're talking about. The mere fact that if you take a derivation in characteristic P and you iterate it P times, you get again a derivation, gives a structure of P Lie algebra on the Lie algebra of an algebraic group in characteristic P. Now, this should have a structure, this is something characteristic 0, should have an additional structure that reflects, that leads to characteristic 0 this operation. Because the reduction mod P of this is the usual Lie algebraic characteristic P. Remember, so this is Lie of G mod P, the usual Lie, because the group law here was such that mod P is just the usual addition. And there is also a bracket that I never talked about that reduces to this actually. So this lifts to characteristic 0 the usual Lie algebra. So there must be a P Lie algebra, a lift to characteristic 0 of the P Lie algebra of this, structure of this. And that's directly related to the Grothendieck P curvature conjecture. It's just that I never found anything.
By the way, that lecture by Moshe, it's recorded. So if you want, you can watch it.
Pardon?
Oh, that's right.
Yeah, the lecture by Moshe is recorded.
Recorded. Yeah, you sent me a link actually, so yeah. I sort of assumed that you will talk about the Tanakian story, but this is something different. Yeah. Okay, so I'll check it out. Okay.
Any other questions? Maybe from the internet?
So it's amazing that, we've been here for a while. And we have questions.
We actually
Okay.
have.
Yeah. Cool. Really.
Yeah.
Excellent questions.
No names,
Well, ratings.
except for her.
Very cool. Wow, that was fun.
Yeah, thank you.
Well, thank you very much.
Thank you.
So that's what Hegner points are.
Pardon me?
That's what Hegner points are. Roughly.
Yeah. Roughly, Hegner points are the images of CM points by modular parametrization. But usually one takes a point like this and adds to it all its conjugates.
Okay.
And then you get a point over Q.
Yeah.
Yeah, and that's
Well, that's what we meant by trace, I see.
Yeah, trace. Okay. Yeah, you take a trace over Q.
Okay.
Yeah.
Thank you.
Oh, sure, thank you.
I leave it to
And
Yeah, but of course, these are the most general Hegner points. But when one studies works of Kolyvagin, you are more specific. You take a certain modular parametrization.
And you actually take Hegner points over an imaginary quadratic field.
Exactly. So the number fields have to be very specific. Everything is very specific.
Yeah.
These are just the most general.
And I was wondering if you could somehow cut them, cut out these Hegner points with an appropriate kind of arithmetic differential equation, and then it might be interesting to study, do something with that way.
Yeah. So that's actually, so I have this paper with Björn Pun, and that's exactly what we do. We find an arithmetic differential equation satisfied by all the Hegner points.
Okay, that's great.
All of them, infinitely many, satisfy one equation as usual. That's and then sure, that helps, because if you have one equation that rules them all, then you can prove finiteness theorems because you show that arithmetic differential equation has only finitely many solutions. So, by using other, something else than the equations themselves. Yeah, you have.
And I'll be able to find this easily, right? Knowing that it's with Poonen and
me and Poonen. We only have two papers, but they are both about this. So, but one is just usual Diophantine geometry, and the other one involves arithmetic differential equations.
Thanks.
You can say goodbye to the...
Oh, goodbye, world. Yeah.